This video is a solution guide to the gas unit practice test. We're going to go ahead and go through all of these problems, showing the work and how to solve them. Okay, so problem number 1 and 2 are both pressure conversions. As you read through this, make sure to identify what pressure you have and what one you're looking for. So we have 1.38 atmospheres, but we want to turn it into millimeters mercury. You start by writing what you have every single time, 1.38 atmospheres. And since this is a conversion, that means I'm going to multiply by a conversion factor, where atmospheres is going to be on the bottom. And since I want to go to millimeters mercury, I can just put that on top. Now this is assuming that I have a conversion between atmospheres and millimeters mercury. And if you look at your periodic table, right here at the bottom, we have this conversion factor where 1 atmosphere is equal to all of these, but specifically 760 millimeters mercury. Now, when you multiply these all through, 1.38 times 760 should give you 1,048.8 millimeters mercury, which you can then round to significant figures if you want to. The second question, same thing. This time, we're looking for PSI, but we are given kPa as the amount of pressure that we currently have. You start by writing what you were given, 103.4, 103.4 kPa, and we're going to multiply with kPa on the bottom and PSI on the top. We just have to have a conversion between these. Well, remember, these are all equal to each other. So if I take this number, 101.325 kPa, and up here I put 14.7, these two are equal to each other. So we'll end up dividing by this number, multiplying by that one, and we should end up with an answer that is close to 15.0 psi when rounded. All right, keep in mind, both of these problems, you're going to end up canceling out these by design, leaving you with the units that you want, and you do need to list your units. Problem number 3 has to deal with manometers. In this case, we've got a diagram for a manometer, and you are required to finish the diagram and also find out the pressure that is either inside or outside the container, depending on how it's written. In this one, we're looking for the internal pressure. So a canister is attached to a manometer, and the mercury is 8 millimeters higher. On which side, though? It's higher on the side connected to the atmosphere. That means I'm going to finish the diagram by shading this in on that side, all the way over to here, and we write down 8 millimeters distance change. The pressure of the atmosphere is 432 millimeters mercury. And all we need to do is find out the pressure in this container. Now, if you look at this, you will see that the pressure is pushing down more on this side than this one is pushing on this side. So this is a higher pressure than the outside. It's higher by 8. So 432 plus 8 is 440 millimeters mercury as our final answer. You could write that in here too. Problem number 4 is an ideal gas problem. There's a tank of oxygen. It doesn't matter what gas it is because all ideal gases behave the same, but it has a volume of 150 liters. The temperature inside is 25 degrees Celsius, and there's 150 moles of oxygen in the tank. What is the pressure in atmospheres? So we start by writing out what our equation is, PV equals nRT, and we list out our variables, P, V, N, R, T, just so we know what we have. We're looking for pressure, so that's my question. The volume is 150 liters. The moles is 150 moles. R is on our periodic table, but it's 0.08206 liters atmospheres over moles Kelvin, and the temperature is 25 degrees Celsius. All of these look correct, liters, moles, and we're looking for atmospheres, except for my temperature is in degrees Celsius, it needs to be in Kelvin. Remember, to go from degrees Celsius to Kelvin, you're going to add 273, and if we add 273, this is going to become 298 Kelvin. Your temperature must be in Kelvin for this to work. Now, if I rearrange my problem, PV equals nRT, I'm looking for pressure, so divide by volume on both sides. Here they'll cancel out. So pressure is equal to nRT over V. We can solve this by doing 150 moles times 0.08206 liters, atmospheres, moles, Kelvin, times 298 Kelvin, all divided by a volume of 150 liters. I know it's tedious to write the whole unit, but you need it. That way you can cancel things out and be sure of things. So here moles cancel each other out. Kelvin's going to cancel each other out. And if you hadn't converted to Kelvin, that's where you would see your mistake. And look, liters would cancel each other out too, leaving us with atmospheres. Now, if I plug this into my calculator, well, I can see the 150s will actually cancel each other out too. If I just multiply these two numbers, in this problem, I end up with 24.45 atmospheres, a really high pressure inside this tank of oxygen. That's the front side of this practice quiz. Let's go ahead and take a look at the back side. We've got two more problems here. Top one, gas stoichiometry. Now this is very similar to the previous problem, except for you're either not going to be given moles, you'll be given grams instead and you need to convert, or you'll be given moles from the ideal gas law and you need to convert those into a different thing using stoichiometry. Let's go ahead and take a look at what we have. What volume? All right, so we're looking for volume. This is what our answer should be in. Of hydrogen gas, this is important, we're looking for hydrogen gas, is evolved when you have 0.87 grams of sodium and water. The gas is collected at this temperature and at that pressure. Let's start by writing PV equals nRT. Because we have pressure and temperature and we're looking for volume, we know it's going to be one of these problems. And if we write this out, PV nRT, now don't just write things in order. This is grams. Are any of these mass? No. But I do see that I am looking for the volume, so we'll put a question mark there. I have 23.5 degrees Celsius. The R constant is 0.08206 liters, atmospheres, moles, Kelvin. And I was given 1.25 atmospheres. Now to solve for the question mark, I still need moles of hydrogen. So the only thing I haven't written down is this, so I must be using this to find the moles. So let's do that. It's a stoichiometry problem, 0.87 grams of sodium. I use this much sodium and it converts over here to hydrogen. So we can look up the molar mass of sodium, because I know this has to be down here and I want to go to moles of sodium. I know that 1 mole of sodium has a mass of 22.99 grams of sodium. 1 mole is what we use for the molar mass. And then the next step is to say, well, there are 2 moles of sodium in my chemical equation. And when I use that, I end up with 1 mole of hydrogen. Now, if I solve this, I'll find moles of hydrogen, which I can place right here. And that is going to solve to be a larger number. We can say this thing's going to be 0.01892 moles of hydrogen. Now, you might be tempted to just round this, but it's not our final answer, so we should probably keep a little bit more than we normally would, right there. And then when I want to solve for volume, volume is equal to nRT over P, which is 0.01892 moles times 0.08206 liters, atmospheres, moles, Kelvin. And then, oh, I didn't convert this to Celsius. Got to add 273 to it. And we're going to end up with 296.5 Kelvin, 296.5 Kelvin, all divided by the pressure of 1.25 atmospheres. Once again, you have to write all your units so you can use them to cancel here, cancel here. I hadn't converted to Kelvin, and that's what helped me to remember to do that. And I'm going to cancel my moles. multiply, 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 then divide, we should end up with an answer of 0.368 liters of hydrogen gas. That's my final answer. Now, biggest misconceptions are going to be if you round this thing to like 0.02, you're going to lose a lot of data getting into here. All right? Also make sure you're converting everything to be liters, atmospheres, moles, and Kelvin. The last question, I won't write anything down, but we'll just talk about it real quick. I want you to describe what's going to happen on a container if we make some sort of change in the gas. And there's a lot of changes we can make. I guess I will write a little bit. I could change the pressure, the volume, I could change the moles or the temperature. And I want you to explain, using kinetic theory at molecular level, what effect is that going to have? If it says a flexible container, that means it's like a balloon, which means that my volume can change. If it is a rigid container, that means it's like a gas cylinder, those metal canisters. They don't change their volume, so your pressure will change instead. But why are they changing? It has to do with the number of collisions. Are you increasing the collisions because of more gas or decreasing them because you've cooled it down? If you made the container bigger, like a piston, with a larger container, they'll hit less often, which should decrease its pressure. You're just going to need to describe whatever situation occurs here based on the amount of collisions that increase or decrease because of the change that you made, and just explain why. Anyway, that's how we go through the practice test. Your actual test will be very similar, so take time to understand each and every one of these problems.